So we have a problem that says Lauren is a very stressed out physics student. In a fit of rage, she throws a 0.5 kilogram physics textbook out of the window of Mr. Corbier's room. So our first part of the question is asking if the kinetic energy of the book as it is thrown is 86 joules, what is its momentum? So let's write down our momentum equation first, which is momentum, which is P is momentum, so we write down P. P equals the mass times velocity. So looking at this equation and looking at the information that we're given, we can see that we only have one part of the equation. We have two unsolved variables. We have 0.5 kilograms for the mass. So what we need to do is find velocity to get the momentum. To find velocity, we can use the other piece of information that we're given, which is 86 joules, and we can use that to find our velocity and then plug it back into the equation. So what can we use to find the velocity? Well, we know that 86 joules is energy, and we know that and it's kinetic energy because the book is moving. So let's write down our kinetic energy equation, which is kinetic energy equals 1/2 mass times velocity squared. So we can just put in our values that we have because we basically have everything that we need except for obviously the velocity. So we have 86 joules equals 1/2 times 0.5 kilograms times the unknown velocity squared. And then we can divide the 86 by 1/2 and then 1/2, and that gives us 344 equals velocity squared. And so now what we can do is square this whole thing to get the velocity by itself. And that gives us a velocity of 18.55 meters per second. And so now that we have our velocity, we can put it back into this equation up here. And let's rewrite it. So the momentum equals mass times velocity. And then we can put in our known values, which is 0.5 kilograms and then 18.55 meters per second. And then we can multiply these values and then we'll get P equals 9.275 kilograms meters times meters over seconds, because the seconds is the only thing in the denominator. So then we have our answer for the first part of the. So the next part of our question is asking, at a certain point, the book's momentum is 7.38 kilograms meters per second. What is the height of the book at this point if Lauren threw it from a height of 2 meters and did 15 joules of work on it? So basically this problem is asking us to use our initial values to find a part of one of our final values, which is height. Height is a component of our final gravitational potential energy. So ultimately we're going to have to find that and then find that one component of it. This problem is going to use our law of conservation of energy because we are dealing with both our initial values and our final values. But basically the law states that the amount of energy present at the beginning of something occurring will equal that the amount of energy present at the end of it occurring. So in this case, the beginning is when Lauren threw it, and the end is at this certain point. At least that's what we're concerned with. So let's kind of think about what types of energy are present right now. We know that we have gravitational potential energy because it says Lauren threw it from a height of 2 meters. So let's write that down. We also know that we had kinetic energy present at the beginning because we have our up here it says kinetic energy of the book is 86 joules because it's moving, so logically we would have energy of movement at the beginning, so we could write that down as well. Oops. And then we know that there's also work being done on it because it says 15 joules of work is being done on it, so we can write that down as well. And this we don't have spring potential energy, which is the other kind that we could have, so this is all going to equal our final energy, which we know that there's gravitational potential energy because it's asking what is the height of the book. So we can write that down as well. And then we know that there is also kinetic energy because it's saying the momentum is this, and if it wasn't moving at all, then there would be no momentum because multiplying a mass times 0 for a velocity will get 0. If you're, we could just reference this equation right up here. So we know that there is kinetic energy, so we could write that down. So let's just write down all our equations. For potential energy, we know it's mass times gravity times height. For kinetic energy, we know it's 1/2 times mass times velocity squared. And then for work, it's, I mean, we already have it anyway, but it would be the force times displacement. Or force times x, whatever. And then again, we have mgh, and then 1/2 mass times velocity squared. So let's just put in all our known values. So for the initial gravitational potential energy, we know that the book's mass is 0.5 kilograms, and we know that gravity is 9.8 meters per second, and then we know that the height initially was 2 meters. And then for kinetic energy initial, we know that it's 86 because it tells us above. And then we know that the work was 15 joules because it tells us right here. And then this equals mass times gravity, so that's 0.5 times 9.8. And then we don't know the height, so we could just put an h for that. And then we have 1/2 times 0.5 for mass times the velocity, which we also need to figure out. And then we need to find our velocity. So we know that our momentum is 7.38, and we know that momentum equals the mass times velocity. So what we can do is use our known value of momentum and use our known value of the weight of the mass of the book, and then we can solve for velocity. So let's rewrite our momentum equation, which is momentum equals mass times velocity, and then we can just put in our values. This is kilograms meters per second, and then 0.5 kilograms times velocity. And so when we divide this out, we get 14.76 meters per second because we're taking away the kilograms. They cancel out. We know that 1 joule is 1 kilogram meters squared per second squared, so we could just change our joules to that unit so we can cancel out the values. And then we have 4.9, and this is meters per second squared. Oh, kilogram meters per second squared, sorry. And then, so when we divide, we get 11.498 meters because everything else cancels, equals the height. So our final question is asking what the force of the book is at this point. So the first thing that I would do, and this is what I always do for forces, is make a force diagram. So we have our book, and then we have the ground. And basically, we can't have a normal force because to have a normal force, it would need to be against the surface because the normal force is the force applied by the surface. So that's out. We don't have an applied force because there's nothing that it's applying to. And we don't really have friction because the friction of air is just so small that we don't really need to account for it. So that leaves us with the force of gravity. Because obviously it's in the air, it's getting pulled down by gravity. So really we only have to account for this force of gravity. So we can say the sum of the forces equals the force of gravity. And we know that our equation for the force of gravity is just the mass times gravity. And we can just substitute our values in. So we know that the mass of our book is 0.5 kilograms, and then we know that gravity is 9.8 meters per second squared. Oops. And then we can just multiply these out. We know that 0.5 times 9.8 is 4.9. And then we know that kilograms meters per second squared is newtons. So we can just write 4.9 newtons. And that is the force of the book.